really missed it. I still haven't recovered. It was hot. Kaena was hot, and I told you it would be, and it was. We had a good time. We saw whales. We saw one albatross on the ground, no chicks. A lot of albatross flying around. Bug seals, number of. So we had an adventure, and we survived. So if I still owe you money, I still have it. So come and see me, and I promise I'll give it fast. And I have sunscreen. Does this belong to anybody? Okay, it goes in the lost and found then.
I'm guessing you guys needed a lot of sunscreen on that day.
Yes, you're right. We needed a lot of sunscreen. There was no wind and a lot of sun. It's a beautiful day. If you get a chance, you should give it a try. Okay, I am really pleased to introduce Dr. Ryan Longman today from the Department of Geography, where he is a lecturer and postdoctoral fellow. Ryan received his bachelor's degree in interdisciplinary studies here at UH Manoa and his master's and PhD in geography. He is the recipient of the Wayne Memorial Award given to the top geography student. He's published a dozen papers, and his area of expertise is the effects of trade wind, inversions, and solar radiation on high elevation climates in Hawaii, and that's what he's going to talk to us about today on climate in general. So help me to welcome Dr. Longman.
Okay, well, thank you for the introduction.
Just wondering, were you in Professor Gio Bang
Jambaluka, yeah.
classes just a while back?
Yes.
Hold on,
I was
hold on.
in-
Save your question, please.
Yeah, it's okay. I gave a guest lecture there recently. So I do teach in the geography department. You know Dr. Tom Jambaluka. He's given this lecture for this class in the past. He's my boss. He's pretty much one of the most revered climatologists in the States, in the state of Hawaii, and he's mentoring me since my master's and my PhD. Really happy to be here today. Climate of Hawaii is a passion of mine. Climate change is a passion of mine. It's a very hot topic, and I'm really happy to share what I know with you. This picture right here, this is the first thing I want to share. This is kind of a view of the Kipahulu Valley. Has anybody been to Hana, Kipahulu, Maui? One of the most amazing parts of this Hawaiian island chain. And this is from a point that's in the Haleakala National Park that's completely off limits to the general population. And one of the lucky things I get to do research, I get to go to some of these places and see them. But this is a look down into the Kipahulu Valley where the 7 sacred pools are. You can see the big island in the back. And I just really love this picture, and I want to share this with you. And doing research a lot of times in Hawaii gets you to go to these really remote and cool places. Okay, so to start this off and ask you a real general question of what is climate before we get going here. So I have a little audience participation, but what is climate?
Basically, it basically tries to explain like what the typical weather pattern is
Typical
in
weather.
that area.
Okay, yeah. Typical weather, average weather, basically is what climate is. So things happen, they change day to day, month to month, year to year, but on average, there's a certain characteristic that's maintained, and that's the climate. All right, so how do you describe the climate of Hawaii? So you have a friend on the mainland, they've never been to Hawaii, they don't know anything about it, you come to school here, or you live here, and they say, well, what's the climate like there? What do you say? What's an adjective you might use? Warm, hot,
Humid.
what else? Humid. Anything else that comes to your mind?
Tropical.
Tropical. Anybody from a really cold place?
Warm.
Warm, okay, so what do you think back there? What's your adjective to describe climate? Awesome. That's what I'm going for right there, okay? So we have all these different things to describe it, right? Okay, what about perfect? Okay, well I moved out here, I was 21 years old, it was 1998, it dates me, but or 22 I think, and I thought it was perfect. I come from New Jersey, really hot summers, really cold winters, and I used to think I was really cool saying it was 2 degrees above perfect. Because I really didn't think there was even any variation during the year. I was always in the ocean. Somebody told me, oh, I don't go in the ocean in the winter. And I was like, winter? Where's winter? I didn't even see it. And I go in the ocean all year round, never change it. But the more you live here, the more you realize there is a seasonal change. If you come here somewhere cold, the first year, so you think it's about, for me, 2 degrees above perfect. All right, so today I'm going to basically talk about the forces that create this perfect climate. And this year is not really the best year to talk about the perfect climate. We had a really hot summer, we have a really dry, windless winter, no rain, and so it's not maybe the ideal year in Hawaii, but I'm still going to call it the perfect climate. I'm also going to talk about the diversity of microclimates, because there's a lot of variation within the island chain. And then I'm going to talk about global climate change, some of the evidence, and some of the deniers of the evidence. And I'm going to wrap this up with some of the research that we see here in Hawaii as far as observed changes go. Okay, so getting back to the perfect climate. Okay, there's 4 factors that make this region of the world, this island chain, what I consider perfect. Okay, the first thing is that we are in the tropics. Now, what the tropics are defined by the Tropic of Cancer and the Tropic of Capricorn. It's 47 degrees of latitude, and what that means is that within that 47 degrees, the sun's radiation will shine directly on the surface of the Earth between those 47 degrees. Above that Tropic of Cancer, Tropic of Capricorn, the sun's rays will never shine directly on the Earth. Okay, there'll always be some type of angle of incidence or beam spreading. All right, so that's why the tropics are called the tropics. So there's a steady amount of insolation shining there. And what that does is it causes very little variation in the annual cycle. So here you have temperature on the y-axis, time on the x-axis. These are several different places in the United States at different latitudes. It might be kind of small there, but this is Monterey, California at 26 degrees. This is Winnipeg, Canada at 50 degrees. And you can see that, as you go higher in latitude, you have this larger variation between the winter time and the summertime. So big swings, it's warm in the summer, cold in the winter. But as you go up in latitude, there's very little variation. Yeah, there's a change, but it's not nearly as pronounced there. Okay, so not only does Hawaii have all this energy, okay, is it really warm, but it doesn't really change much over the year because we are so close to the equator. Okay, we are in the tropics. And now this is 26 degrees. Oahu's at 21 degrees, so you can imagine that variation is even smaller. Okay, the second thing that makes Hawaii one of these perfect factors is that it's surrounded by ocean. The ocean has a very high heat capacity. It means that it can absorb a lot of radiation. Land, on the other hand, it heats up, cools down really fast. Ocean takes a long period of time to heat up. It can absorb lots of energy. That's because there's lots of mixing going on in the ocean. The albedo is higher, so it reflects more energy. And the land, there's no mixing or anything, so the land just absorbs the energy. And on the ocean, there's horizontal mixing, there's vertical mixing, lots going on that kind of distributes that energy. So if you look at a place here like Dallas and San Diego, which are virtually at the same latitude, okay, there's San Diego, there's Dallas, same latitude. This is the temperature variation over the course of the year again. You see that San Diego has a very little, much less pronounced variation than Dallas does over the year. And that's because San Diego is right next to the ocean. All right, so the ocean takes up a lot of that heat. There's evaporative cooling going on. It keeps things pretty mild. Same thing with Los Angeles, San Francisco, all of those areas along the California coast have very little variation. Okay, that's the West Coast. The East Coast is a different story. I'm not going to get into that in the lecture here, but this is the example for Hawaii. Hawaii is surrounded by water, and the ocean has a very moderating effect on the temperature. Okay, the third factor is atmospheric circulation. So we have these large circulation patterns occurring across the atmosphere. Some of you may have taken a Geography 101 or early class, heard about the Hadley cell circulation. These are these circulation cells. What happens is the air is lifted at the equator because it's low pressure there. Air tends to lift in low pressure areas. It's then pushed poleward in the upper atmosphere, and then it descends back down the subtropics. All right, and then that air is pushed along the surface from the subtropics back to the equator, where it lifts again. And we call this Hadley cell circulation. It's this giant atmospheric cell here, and it operates in both hemispheres, and it circulates the air. This right here is our trade winds. Okay, they're a consistent thing. You have low pressure here at the equator, and high pressure here at the subtropics. Everybody's heard of the Hawaiian High. That's a result of this atmospheric circulation. Now, because of this circulation, we have things that affect our moisture. Now, we've already talked about why the temperatures are warm because of the latitude, and why they're moderate because they're surrounded by ocean. But climate exists. There's two factors that make up climate. There's temperature and there's precipitation. So we know it's warm here, but how do we get our moisture? Well, if you look at this map here of annual precipitation across the world, the green areas are really wet and the white areas are really dry. So what's a really wet area? You just off the top of your head here, look at it. Brazil, okay, Amazon forest. What latitude are we at right about here?
Close to the equator.
Yeah, right about the equator, okay? So that's where you got your low pressure, okay? You look across here where the equator is, you know, you have really moist areas. Now what's a really dry area? Sahara Desert, okay? And what latitude is that at about?
About 30.
About 30 degrees. That's where the descending area is from the Hadley cell, okay? So if we pull this little strip out here, we can see that, you know, Sahara Desert, okay, central Mexico, and, you know, Hawaii are all kind of in this really arid area. And that's because the Hadley cell has this descending air, this high pressure, and this is basically an arid zone, right? And that migrates a little bit through the year as the subsolar point moves and our intertropical convergence zone, that area of low pressure, it's not fixed at the equator. It moves, it migrates, so it's not, you know, set in stone, but in general, those are really dry areas, all right? And Hawaii, if you've gone to the leeward sides, or you know, you've been on Kihei or Kona, these places with the taller mountains, you see that they're really dry areas. All right. So, if Hawaii, and I didn't bring up this here, this has to do with the monsoon. That's why you have some wetness there. I'm not going to talk about that today. What I want to ask you though is, if we're in this really dry latitude, okay, how come we have so much rain here? Okay, we've all been to the, you know, the windward sides of the island. We've seen how green and lush it can be under normal conditions. How come we have rain if we're in this really dry latitude of descending air?
Trade wind?
Well, the trade winds are a part of it. But what's the other factor? The mountains, okay, the topography of the island. And this is our fourth factor of why Hawaii has this different climate. All right, so what happens is the sun's energy shines down on the ocean and it evaporates water. Okay? This makes the air really moist, saturated air. Then the trade winds come and they take that moist air that's all around the ocean and they push it up the mountain. Okay, it just comes right in contact with the mountain and that moist air lifts right up the mountain. And as air lifts, moist air, its ability to hold moisture decreases, and then that moisture will condense out from a vapor to a liquid, which is a cloud droplet. All right, and those clouds will start forming what we call the lifting condensation level. That's the point on the mountain where the amount of moisture in the air is equal to the possible amount the air can hold, and that's when clouds start forming. And they form in a particular area about 700 and 1,000 feet. And then this top here, the trade wind inversion, which Cynthia mentioned that I studied for my PhD, it kind of caps the clouds at the top. And I'll explain that a little bit more in a second here. But this orographic lifting kind of produces this steady amount of rainfall. We have a fog zone, and this is where our tropical montane forests are found on the higher islands. And we get this orographic rainfall on the leeward sides. And if you were to take away the mountains, the average amount of rain that you get on the open ocean is 700 millimeters a year, which is a very small amount of rainfall. Okay, some areas on Maui are getting over 10,000 millimeters a year, to give you an example of what the ocean compared to that. So almost 16 times as much as that. So if we didn't have mountains here in Hawaii, it would all be dry desert, look very similar to Kihei or some of the Kona regions. The mountains are what give us a majority of the rainfall. There are things like cold fronts and things that come through in the winter that do give us some rainfall, but probably about 80% of the rainfall we get is due to orographic lifting. All right, so those are the four factors that make up this kind of ideal perfect climate. But we all know that the climate is varied very much in Hawaii. There's no, one place that is exactly even the same as the other. The Big Island, for example, has 4 of the 5 major climate classifications in the Köppen climate system. It even has the tundra or the polar climate at the 2 highest mountains, Mauna Loa and Mauna Kea. So to say that Hawaii is tropical, yeah, it's classified as a tropical climate, but we actually have polar characteristics at some points on the islands. And if you look here at what tropical means, this light green and dark green areas, you can see that really only a little bit of the island is actually even tropical. Okay, only this outer kind of windward and then south westerly thing here. You have the desert climate, you have this temperate climate on the up slopes, and you have the polar climate there. So to say that Hawaii is tropical isn't really accurate. There's a lot of things going on, especially on the Big Island. Okay, so what makes this climate diversity? Well, there's 2 things. One is that the horizontal differences are affected by this windward-leeward aspects. trade winds are blowing northwest across the islands. They're going to come in contact with part of the islands, and these larger mountains are going to deflect the winds and cause these discontinuities between, you know, what's happening with this more moist air coming in contact with one side of the island and not the other. The other thing is the vertical differences, and that's basically a result of the trade wind inversion. So I'll explain both of that in a second. But getting back here to our Hadley cell, we have this downward descending air. We have this really high pressure that exists to the northeast of the Hawaiian Islands. So they call it the Hawaiian High. It's semi-permanent, which means it's there pretty much a majority of the time. There are things that happen, that disturbances that come through that disrupt this normal flow. But for the most part, we can count on that being there, especially in the summertime. And air will always move from high pressure to low pressure, like we saw here on this little schematic here. It moves across. So it moves from high pressure to low pressure, so from north to south. And then the spinning of the Earth is called the Coriolis effect. That deflects air to the right, and that basically gives us our northeast trade winds. All right? And that's why we have this kind of consistent, about 80% of the year, have this steady flow. And these winds are pushing that moist air up the mountains on the leeward side. So this moves, and you know, there changes through time a little bit, but you know, for the most part, this is a general idea of what happens with our trade winds. All right, so that's the horizontal differences. You'll get wet areas on the windward side and dry areas on the leeward side, in general. Okay, so the trade wind inversion, resolving these vertical differences, and I think that the trade wind inversion is something that, before we go any further, how many people have heard of the trade wind inversion? Okay, so
I heard the term.
What's that?
I heard the term.
The term, yeah. So a few people have heard of it, but it's a very prominent feature in Hawaii. You've all seen it before, but you may not have known what to call it before. All right, so I'll get to a picture of it in a second. But the trade wind inversion, you know, also ties back to our atmospheric circulation. So what happens as you go up in elevation? What happens to temperature? It gets colder, okay? And what happens when you go down in elevation? It gets warmer, okay? I know you guys are above these kinds of questions, but just humor me here. So if I go up in elevation, a temperature cools. And if I go down, I get warmer. Now, because the air at the surface of the equator is warmer than the air at the surface of the subtropics, that air, even though it's traveled in the upper atmosphere, as it cools, or as it warms, that cool air warms, it warms at a slightly different, same rate, but since it originated a little bit warmer from the tropics, there's a discontinuity in the cooling and the warming of these two different air masses. And what that discontinuity does is it causes this little tiny inversion that happens over a few hundred meters up on the mountain slopes. And they call this temperature inversion. And as air rises, it will only rise if the air above it is cooler. So this is the inversion, and these are the clouds. The clouds will be capped. Vertical development will be capped at the top of the inversion. And that is basically what the trade wind inversion does. It causes really dry, stable air above it when it's present. All right, so here's tying a few things together. Here's a schematic. This is kind of a schematic of Maui, I would say. And we have our trade winds that are pushing clouds up the mountain. They're orographically forming. We have this upslope breeze that's occurring. It's also producing clouds. It's not really strong enough to produce a lot of rain clouds, but if anyone's lived in Kihei before or been on that side of the island knows that it gets pretty cloudy over there due to an upslope breeze. Not very rainy. These are really where the rain clouds are. And these clouds will develop all the way up the mountain in the absence of the trade wind inversion. But because of this downward descending Hadley cell circulation, the inversion is present, and then this area up here is basically capped from the clouds, and it's really dry up there. Has anybody been up top Haleakala? Okay. How about Mauna Kea? All right, so you know what it's like up there. Herman, what's it like up there? Cold. Cold and no trees and dry and moisture. Okay, you don't have a lot of trees up there because there's not enough moisture to support that kind of growth. All right, so this is basically what the inversion looks like. All right, so this is the slope of Maui. This is on the North Shore, and you can see that it's got this really nice blankety pillow. So everyone's gone inner island, I'm sure, and you've seen this from outside of the plane. That nice soft blanket of clouds. You want to lay on it like a Care Bear. But you know you'd fall to your death if you did. But anyway, that's the inversion. So you've seen it your whole life. You've gone up to Haleakala and you're driving up and you're like, oh man, it's cloudy today. Bummer, I was hoping to see the Big Island. And then you get up there and you're like, wow, it's crystal clear. It's because you've driven through the inversion. Right? So most of you, probably all of you, have seen this inversion before. All right? And this is the site I was actually here last month. This is called Frisbee Meadow. It's on the North Shore, about 7,000 feet up. And this is a little research site here. They study a bunch of different things going on there. We're studying drought now in the lab I'm in. And this is a great picture of the inversion as well. You can see that the clouds really, you can see the ocean off in the distance. So, the clouds really only kind of hang around the mountain at that point.
And so that's because there's warmer air above the clouds from Hadley South?
Yeah, so no, that's because there's a discontinuity in the rate that the air is cooling and the air is warming. So there is a temperature increase, but you really wouldn't feel it. If you were going up, it's just a small, but it's just enough in the atmosphere to stop the clouds from rising above. Because clouds will only rise at a point where the air above the clouds is cooler. If it's warmer, it won't rise. So it's a discontinuity in these two air masses, as one's cooling and one's rising, that just causes this. So you see this, we look at the radiosonde data, which is a weather balloon that's released from Hilo and Lahui every day, twice a day, and it takes a vertical profile of temperature. And this is how we calculate the inversion. We look at the temperature profile and see where it actually goes from cooling to warming. And you can catch that in a really small window, but it only happens over a couple 100 meters at most. Okay, so this vertical and horizontal differences causes this great difference, this diversity in climate. This is a rainfall map here. The darker colors are the wetter places on the islands, and the lighter colors are the drier places. So Molokai, 13 feet of rainfall on the windward side, 20 feet on Hilo, 23 feet of rain on Oahu and the Kolaus, 22 on East Maui, 30 feet in West Maui Mountains, 33 feet Mount Waleale, and then you go to 11 inches of rain in Kihei. So some really stark differences there. And less than 10 inches here in this little alcove. This area is one of the drier places in Hawaii. It's basically shielded by 3 volcanoes here. All right, so where's the wettest spot and the driest spot on the island? Anybody know where
The wettest spot it was somewhere on Maui, I believe.
Yeah, it's on Maui. It's on Big Bog, Maui. It's basically 34 feet of rain a year. We have a climate station there. Good question in the back? Oh no. And then the driest spot, you know where that is?
Was it that little place you just showed us on the Big Island?
No, it's not there. Think about what I just showed you before in the last slide. The high elevation place.
The Frisbee.
It's the highest elevation in Hawaii.
Mauna Kea.
Mauna Kea, yeah, that's the very driest place with about 8 inches of rainfall a year. Okay, so the wettest and the driest. I mean, they're, Hawaii is an amazing place. If you were in, say, let's just say, not picking Kansas or Nebraska, or somewhere in the Midwest, I don't want to single out any state here, and if you were to go this far in distance, how different would the rainfall actually be? I mean, what if you, took an X number of miles between this and this? Okay, you can go from 8 inches to 34 feet. Hawaii is an amazing place to study the climate because the gradients are like nowhere else in the world. Okay, mean annual temperature. All right, so obviously, the places at low elevation are going to be really warm, and places at high elevation are going to be really cold. But again, these gradients, how do you go and drive? Well, if you're, it's a little bit of a drive to get all the way to Mauna Loa, but if you're going up to Mauna Kea here, it would be a pretty significant, decrease in temperature over a very short distance. So Hawaii is this awesome laboratory where you can study all kinds of different aspects about, different climate studies. You can control for these different things, temperature, relative humidity, rainfall, along these gradients that are just like nowhere else in the world. Relative humidity, again, some very stark differences. So 45% relative humidity at top of Mauna Loa and 98% outside of Hilo there. So again, over very short distances, very big contrast. So why is relative humidity so high or so low at the high elevations? What's going on there again?
The inversion is keeping moisture from getting up.
Yeah, there's no moisture. So even though it's cold, and relative humidity is a function of the ability for air to hold moisture and the amount of moisture that's in it, even though it's cold, usually if there was no inversion, the highest relative humidity would be at the highest elevations, because it'd be so cold, it can't hold any moisture. But there is no moisture, so relative humidity is very low. So Hawaii is different in that regard. People that don't know about the inversion that come to Hawaii, they're hard for them to believe that the highest points have such low relative humidity, but it's a result of the inversion. It's a very unique feature of the islands. All right, so we have these atlases as part of this project during my PhD. I wasn't for my PhD, but some of my funding came from developing these climate atlases of Hawaii. The rainfall atlas was already done, but there's lots of different microclimate. If you guys are doing a report or want to characterize an area, if you want to talk about the climate there, all this information is there. For every single variable you could actually think of for climate. So just a little food for thought there if you need to, pull a little depth into some of your research you're doing this semester. Most of the sites look like this. There's information on the site there, some methods. There's also an interactive map. You can click over any spot in Hawaii. You can get a rainfall value for the year. You can get it for 24 hours a daily rainfall estimate as well. Or sorry, a mean daily, so a diurnal cycle, so how much rain is happening over the course of the day. You can do that for all the other variables. You also, anybody do GIS here? A couple people? Okay, so if you want to bring in some of this climate data into your projects with GIS, all of these layers are available for download as well. So for all these different variables. So it's a pretty awesome product and something that I was proud to be part of. All right, so now I'm going to transition in here and talk a little bit about global climate change. This is something that I've also been studying in addition to my PhD research. This is something hot topic in the news, a hot topic that you see people debating about it. It's an election year. You hear this come up every so often. It doesn't come up enough actually. But global climate change. What is it? What's happening? What's the evidence? Who's supporting it? I think these are all important questions. Is it natural or anthropogenic? Okay, an often argument of the denying campaign. Okay, yeah, climate's changing, but it's not because of humans. It's because of a natural variability. So what is natural climate change? Does anybody have an example?
There's a big volcanic eruption that causes global temperature to cool for a couple years.
Yes, that is definitely a bit of natural variability. Anybody else know something else? Milankovitch cycles over very large timescales. Yes, the climate actually fluctuates on very large timescales due to these very large cycles of 100,000, 30,000 to 100,000 years. But in recent time, thinking more recently, there's something going on.
Like ice ages?
Well, yeah, all right, so now we're thinking more of longer time as well, all right? And that has to do with the Milankovitch cycles. So the natural climate variability of volcanic eruptions, changes in solar irradiance as the sunspot cycle, and also the effects of ENSO and PDO. So ENSO is the El Nino Southern Oscillation. Anyone hear about that? Okay, that's also all in the news quite a bit these days. And the PDO is the Pacific Decadal Oscillation. There's the AMO, which is the Atlantic Multidecadal Oscillation, the PNA, the Pacific North American Index. There's a lot of acronyms. And when you're doing research in climate, you can always test your stuff against one of these different acronyms and see what the results come up. But in Hawaii, these are the two that are talked about the most, particularly the ENSO, which is one of the strongest factors. And what the El Nino is, I'm not going to talk too much about this, but it's natural variability that changes the pressures in the ocean. And what that does is changes the winds. And then as the winds change, it changes the movement of water, which changes the distribution of energy. Okay, so a real simple way of characterizing ENSO. It originates here in the central South Pacific. And the two phases of it, well, there's three phases, but the two major phases are the warm phase, which is the El Nino, and the cool phase, which is the La Nina. So during El Nino conditions, the trade winds break down a little bit, as you can probably tell, just because we're feeling that daily here in Hawaii. The trade winds break down a little bit; they're a little bit less. And what that does is it stops all that warm ocean water from being pushed across the ocean, because the trade winds blow from east to west. And when the trade winds stop, that warm water kind of sloshes back. Okay, it's not pushed to the Pacific Rim. okay, the western rim. It sloshes back. And that causes warmer sea surface temperatures in Hawaii and in other places. So there's what they call teleconnections. It gets, for Hawaii, in this area, it's dry, it's wetter in the southeastern part of the United States. Okay, different areas, are either wet or dry or warm or cold. And then the La Nina, which is, kind of when the winds are strong, then we get some other different opposite effects. So El Nino is not specific to any one particular area. You might have drought in one area, you might have really wet conditions. But if we focus on Hawaii, okay, we see that during the El Nino conditions, it's predominantly dry. So does anybody agree that it's been dry the last couple of months?
Yes.
Yes, it's been really dry. Take a look out the window. Look at Diamond Head compared to what it was even this summer. It's been extremely dry. Actually, I looked this up yesterday at the Hawaii Drought Index monitor. You can always look this up at this website here. It showed that 100% of the state was abnormally dry, and that a small portion of it was in moderate drought, and then actually some places were experiencing severe drought. All right, so actually 100% and then 7%. I have those numbers there. So statewide rainfall has been 68% below normal. And then in January, which was the driest month, we have had a little bit of rain in February. It was 90% below normal. So, I mean, as far as the science goes, we know that during El Nino it gets really dry here, but this is actually, a very strong El Nino. It's actually the second strongest El Nino that we've had in recorded time. The other one was in the 97, 98 year, and people were around then, but that stands out as one of the most significant climate years in history because of all the major impacts that it had there. Does anybody know where El Nino comes from? The word, what does El Nino mean? The boy. All right, well, this happened around Christmas time, December, January, February, and when the El Nino happens, you have the waters are warmer, okay, there's a lot of more fish on the eastern seaboard, and this happened in South America, and they attributed it to the boy child of the coming of Christ, and that's how it got its name, the boy. And I don't know, La Nina with the girl, I don't know if that meant no fish in cold waters, but how they came up with that, I don't know. But anyway, that's where it originated from. That's why we use those terms, because it originated with major signals in the southern eastern coast of South America.
You said the 97 to 98 El Nino was the strongest, yeah.
Yes.
Was it a super dry year during that El Nino too?
Yeah, extremely dry. Yeah, major droughts. Well, for Hawaii, everywhere is going to be a little different. Okay, so that was talking about the natural variability. Okay, so it was mentioned that climate changes over these very long time scales. It also changes on these short interannual time scales, and that's the ENSO PDO signal. Okay, year to year, El Nino lasts between 2 and 7 years. It could last, it could be gone next year. There's a little bit of predictability to it, but it's not something that lasts for 100 years. All right, now forest change. Forest change is how humans, or anthropogenic change, how humans are affecting the climate, and they're affecting them through the emission of greenhouse gases. So this is looking carbon dioxide, methane, and nitrous oxide, which are the 3 major greenhouse gases, and you can see that the x-axis we're starting at 0 and going to about 2010 here, maybe, and you can see that the gases were pretty much constant, a little variation, and then at the turn, the Industrial Revolution was here. We saw this dramatic spike. It's called the hockey stick curve. If you flip it around, it's a hockey stick, and this is Michael Mann came out with the temperature curve that kind of alerted the world to global warming, and all of these things. You look at population, you look at pollution, you look at gases, almost everything has a hockey stick effect because the world has changed so much since the Industrial Revolution and our ability to produce but also to pollute. So this is looking at CO2 concentrations from 100,000 years ago, and you see that there were some oscillations over time, but in general we're still kind of at unprecedented territories here. And in January 2016, we were at 402 parts per million. A year ago, 399. And on May 9, 2013, we actually was the first time we went above 400. Now, what was it pre-industrial? Anybody know?
When was pre-industrial?
Pre-industrial revolution, what was the CO2 concentration? 280, okay. So pre-industrial was 280. We're at 402 as of last January. So we are increasing at a rate of 2.89, or 3 parts per million a year. All right, so it's been a significant change over time. And we've seen that in actual temperature record. So this was released by NOAA at the end of 2014, and this shows you departures. So a departure is an anomaly. An anomaly is a departure from some type of mean. So the 20th century mean goes from 1900 to 2000, and these little points on the graph represent whether it was hotter or colder than that particular mean. So you can see that there's definitely some variations over time, but once you get up into this area, once you get to 1970, 75, you see that you just have positive anomalies. So all these points it means it was warmer than it was compared to the average. And if you look at 2016, or 15, it was actually the warmest year on record. So this is looking at 2015 was the first warmest year, 2014 was the second warmest year, and then 2010 was the third warmest year. So out of the last, if you look at these points right here, I can't see that good, 2013, 10, 14, 15, you have 4 of the hottest years on record occurred in the last 6 years. And we have an El Nino this year, but this was La Nina conditions over here. So we really can't blame, this on natural variability. This is a clear signal of anthropogenic influence in this time series here. And if you go back here, the earliest date you get, let's see, 97, that was the El Nino year. Those are particularly warmer years, or sorry, cooler years, but for the globe. And you can see that, the earliest date you have on this whole thing, correct me if I'm wrong, is 1997. So whatever, 20 of the warmest years occurred since 1997. It's striking evidence that the climate is warming. The things that cause change, that cause warming in the planet, basically warming is a result of extra energy trapped into the system. They call that radiative forcing. You're forcing the planet to get warmer because of extra energy that normally would have left the planet is now staying in there. And things that hold energy into the planet are greenhouse gases. So this right here is from the IPCC report. And if you look at this line right here down the middle, okay, this would mean that there's no forcing going on. So everything to the right means a positive forcing. It means they're keeping energy in the system. Anything to the left means that things are happening to reduce energy in the system. So our greenhouse gases, our CO2, our N2O, and our methane here are all positive forcing. So more energy is staying in the system because there's more greenhouse gases. Then you have things like land use. Well, if you cut a bunch of forest, what do you do to the albedo? Albedo is the reflectability of the surface. But if you cut the forest down, what happens?
It's being absorbed.
What?
It's not being reflected, right?
Yeah, well, it depends on what the color looks like. You could reflect it more. You could reflect more energy out. You could absorb more energy. But in this case, globally, cutting down forests and changing land use is actually adding to the albedo. So it's increasing the albedo, so you're getting more energy reflected out. It has a negative effect. But it also adds greenhouse gases to the atmosphere, so it has a positive effect on that end. Clouds, the albedo effect, contrails from planes, these have small effects as well. During the September 11th, when they stopped air travel for 3 days around the world, basically, they saw a huge spike in solar radiation occur, and temperatures were really warm those 3 days because all of the planes, all the emissions from the plane, they have the contrails, they have particles, aerosols that clouds form, that reflects energy, and as a result of the planes not flying, you got a huge influx of actual energy, and temperatures got warmer for those 3 days. So some of the things we're doing to the planet are actually having this cooling effect. So if we were to stop all polluting, we would actually see a huge increase in temperatures because of the changes in albedo and changes in contrails and things that are actually doing things to reduce the amount of energy coming in. And then the only thing we have here for natural, because the volcanoes don't really make that big of an impact in recent time here anyway, is that solar radiation. And you have just a little bit of a positive force in there. So science has figured it out. This is your net anthropogenic amount, and it's basically holding almost an extra 1.5 watts of energy into the system. And that's resulting in almost a 1 degree Celsius increase in temperature. Okay, so the planet is already warmed almost by a degree already. Okay, so science has concluded this. This is science not saying yes or no, it's saying with 95% confidence that anthropogenic climate change is real and that the planet has warmed by almost a degree and will continue to warm if something isn't done about it. Okay? Science, as a consensus, has concluded this. So if science has concluded it, right? Science concluded it, we better do something about it, right? The U.S. is the leading country in the United States, in the world as far as growth, as far as economic development. We should be the ones that say, oh, if science concluded it, okay, what are we going to do about it? Well, they vote like any good government does. They vote on things. Well, Sheldon Whitehouse put out this bill. This is just in January, that climate change is real, and in the Senate it won. Okay, 98 people said yes, it's real, and only one person said it wasn't. Okay, so that's a really good step in the right direction, yeah. Well, Brian Schatz from Hawaii added a little stipulation in his bill that said that climate change is real and human activity significantly contributes to climate change. And that one failed. So what's happened in the world of climate denying is that they had to give a little bit of leeway. They had to finally say, well, all the scientists are admitting it's happening. We really can't just keep saying that it's not happening because all these smart people are saying it's happening, every one of them, except for the ones that are being paid by ExxonMobil to say it's not, which is pretty much less than 1%. But what they're not going to concede to is that it's happening as a result of humans. What they concede to is that it's happening, but it's still happening as a result of natural variability, which science has concluded that that's not true. Okay, so the global climate change science, basically every scientist in the world agrees that it's happening, and the deniers are sitting on a very small side there, but they have a very heavy weight. It becomes this very heated debate. Is it happening? Is it not happening? And I think that's it's a major problem because science has already concluded it. Why are people still arguing whether it's happening or not happening? And I'm going to get to that because there's a pretty easy answer. Our elected officials, okay, Mitch McConnell, the Senate Majority Leader, he has blatantly says that climate change is a hoax. Okay, Senator Jim Inhofe from Oklahoma, he's the chairman of the Environmental and Public Works Committee, and he has written a book that climate change is a hoax. So these are the guys that are leading the fight on climate change. They basically say it's a hoax. Now, why are people denying it? Okay, well, this is a really interesting study that they did here, and they found that over 56% of Congress either deny or question the science behind climate change. And this map right here is showing you, based on color, how many representatives, either Congress or House of Representatives or Senate people, deny climate change in a given state. So the darker red mean that 51% of the elected officials deny it or question it, and the gray means that no one denies it or questions it. Okay, well, it's very simple put together. 170 elected representatives in 140 Congress have taken over 63.8 million from the fossil fuel industry, driving carbon emissions, which cause climate change. So, it's very simple. The people in the red states that deny climate change are receiving money from the fossil fuel industry for their campaigns, for whatever case might be. They're lobbied in that direction. They take a position based on that. All of these states have nobody that denies climate change in their thing, and not one of the people, one of the Congress, Senate, or House of Representatives, anybody in those gray states has taken $1 from the fossil fuel industries. Okay, so not all that information's up on here, but if you want to check out this website, it's really cool because it just kind of it puts it together. Why would all these people be denying climate change? They're smart people. They're elected. Well, it's a problem with our system. It's a problem with how people get elected. They need money to get elected. It's a very big fundamental flaw in the whole system. Just a little list here of some of the names that I just pulled up, and some of the people, some of the actual amounts they've received from natural, from oil and gas industries over time. There are a couple of people that are actually, well, one current person in the GOP primaries, and Rand Paul dropped out, but almost $1 million, in oil and gas industries. I heard Ted Cruz. I'm not in any way going to want to shape your political beliefs, and I'm not going to tell you who to vote for. But I heard him on NPR. Anybody hear Ted Cruz on NPR? It was about a month ago. Anybody catch that? Anyway, I heard him talking about climate science, and I was driving in the car with my wife, and I was like going to have a discussion in my class, and I was like, oh, turn this up. I really want to hear this, for my discussion tomorrow. And I got about, I don't know, maybe 30 seconds in, and I was like, I just had to turn it off because it was such wrong science. It was pure, utter lies that were coming out of this man's mouth. And I'm sorry if you support him as a candidate, but as a climate scientist, neutral to all politics, it was just absolutely wrong information coming out to NPR across the thing. And for people probably nodding their head like, oh wow, he makes a good point there. But it was just wrong, and I had to turn it off. Anyway. So, it's depressing, I know. Is there still hope? All right, well, has anybody heard of the COP21? COP21, yes, okay. Anybody else? Big meeting in Paris this last December to address the issue of global climate change. The COP is the Committee of the Parties, it's the United Nations Framework on Climate Change, and I won't go into all this here. But basically, the Kyoto Protocol, which was in 2001, they started to try to address climate change then. And a large number of countries signed on to this, but this was under the Bush administration, and the US said we're not going to participate, Australia said they're not going to participate, and it basically squashed this idea of dealing with climate change at that point, because nobody in the world is going to sign on to something that involves saving the planet and not polluting if the #2 polluter in the world, which is the US, doesn't sign on as well. So that was a failed attempt. But this Committee of the Parties, COP21, met in December, and 189 countries have committed to this, keeping global temperatures below 2 degrees, limit the amount of greenhouse gases the Earth can absorb naturally. Rich countries are going to help the poor countries adapt to climate change. And this was agreed upon. They had to go into extra time here, but 189 countries came together, said climate change is real, and we are going to do something about it. And they have until April of 2016 to actually sign this for all that it's worth. So we'll see what happens, but there is still hope that there could be some global cooperation. Is this class 20 after it's over?
Yes.
Oh, is that clock right? Yeah. Oh, okay. So I don't want to keep you guys. That's an awful part of having a guest lecture. It keeps you longer than you have to be there. I have a ton more stuff in this presentation, but I'm not going to go too much longer. I just want to show you that these are the future scenarios. We are currently on this path here to have 8 degrees Celsius warming. We want to try to cap it at 2 degrees, and I think that's going to take a lot of effort. And as you go into your lives here, and as you make a choice politically to choose a candidate, I think that you should always look at their stance on climate change and see if they feel that there's something needs to be done about it. Support the people that want to make the world a better place and want to address what I would consider, as a climate scientist, the #1 issue that humanity is facing and has ever faced. And we're only seeing it's happening now, and we're only seeing the very start of what's to come. So thanks for your time, and if you guys will have some questions, I'll be up here.